question 64 in chapter 11 in our physics textbook. It says that if we have an engine that does 10 joules of work and exhausts 15 joules of waste heat, it wants to know in part A what is the engine's efficiency, and in part B, if the cold reservoir temperature is 20 degrees Celsius, what is the minimum temperature possible in degrees Celsius of the hot reservoir. So to do this problem, what we need to do is record the information we have. So it gives us work, which they say is the 10 joules. It gives us our waste heat, which is 15 joules, and it gives us our cold reservoir temperature, which is 20 degrees Celsius. And we're going to indicate our cold reservoir temperature as T2 for this final equation here. But to do part A, what we need to do is solve for, it wants us to find what the engine's efficiency is. So to do that, we know that equation to solve for efficiency is efficiency equals work over the heat given to the engine. And so this is our final equation we want to get to for that first part. But we don't have the engine given to the heat given to the engine. What we have is the waste heat and the work. And so what we can use is this equation here, which is the heat given to the engine is equal to the work plus the waste heat, and that should give us our heat given to the engine, which we can then plug into this final equation here, which will solve for our efficiency. So to do that, we just take our work, which is 10 joules, plus our waste heat, which is 15 joules, give us our heat given to the engine. So what we end up getting is 25 joules, which we then will plug into this equation, and we'll plug in our work again. So we'll get 10 joules divided by 25 joules, which gives us an efficiency of 0.4, or if we want it in a percentage, all we have to do is times by 100, which would give us 40%. And so that's our answer for part A, which is what is the engine's efficiency. And so for part B, that's the question that wants us to find the minimum possible temperature for the hot reservoir if the cold reservoir is at 20 degrees Celsius. So to do this problem, it's a little bit more complicated, but we have this equation here that we can use, which is our efficiency equals T1 minus T2 over T1. And to solve part B, what we need to do is input the information we have into this equation and basically solve for what we don't. So we have our T2, which is the temperature of the cold reservoir, which is in 20 degrees Celsius. But since it's in degrees Celsius, we actually need to convert it to Kelvin in order to have it in the units we need for this equation. So what we need to do is convert our 20 degrees Celsius to Kelvin. And when we do that by adding 273.15 to our degrees Celsius value, which will give us 293.15 Kelvin. And so now that we have it in Kelvin, we can use it in this problem for our T2. So we now have T2 in this final equation, but we also have our efficiency, which we solved for earlier for the engine's efficiency, which we got 0.4, which we can also enter into this equation. So if we do that and enter in all the stuff that we have, we get 0.4 equals T1 minus our 293.15 Kelvin divided by T1. And so now what we want to do is basically get it to where we only have one T1 on one side and can just solve for T1. So what we can first do is times by T1 to get it off the bottom, which will cancel on this side. We times by T1 on this side, which will give us basically 0.4 T1 equals T1 minus our and 93.15 Kelvin. So now what we can do is we have 0.4 T1, and on this side we basically have a 1 T1 because there's no number before it, so it's just like basically 1 T1. So what we can do is minus the T1 from this side minus the T1 from this side, which will give us, it will cancel out on this side, and then if we do 0.4 minus 1, we get a negative 0.6 T1, which is then equal to the only thing we have left on this side, which is the negative 293.15 Kelvin. And so now at this point, all we need to do is get T1 all by itself. So we divide by negative 0.6, divide by negative 0.6 on this side. This will cancel out. And what we should get when we divide negative 293.15 by negative 0.5, we should get 488.58 Kelvin, which is our T1. And we're not quite done because it says that it wants it in degrees Celsius. So we have it in Kelvin. So what we need to do at this point is basically convert our T1 from Kelvin to Celsius. So what we can do is take the 488.58 Kelvin minus the 273.15 we used to convert Celsius to Kelvin. And if we minus the 273.15 from this, it will convert it back to Celsius. So we minus the 273.15, which will give us 215.43 degrees Celsius. And so that's our answer for part B in question 64. So part A, we got that the efficiency was 0.4 or 40%, these values here. And then in part B, the answer is 215.43 degrees Celsius, which is what the minimum possible temperature for the hot reservoir would be if the cold reservoir temperature was 20 degrees Celsius. And that's how you would do question 64 in chapter 11 of our physics textbook.